All right, let's continue our discussion of matrix multiplication. I'm going to demonstrate actually block multiplication. Um, so for example, suppose we have two matrices A and B. Okay, we can partition A and B into, I'm going to show a 2 by 2 partitioning here, but the partitioning could really be of any size. So it's really just separating the matrix into smaller submatrices. So A1 and A2 here would have to have the same number of rows. A1 and A2, since they're right above each other, would have, I'm going to call this one A2, this one A3. A1 and A3 would have to have the same number of rows. A1 and A2 would have to have the same number of columns. And A4 would have to have the same number of columns as A3 and the same number of rows as A2. But this can be a somewhat, arbitrary partitioning of the matrix. Here I'm showing a 2 by 2 partitioning, but it could be of any dimension. It could be a 2 by 3 or 3 by 4, whatever. It's somewhat arbitrary. And then for B, and I'll show the same, a 2 by 2 partitioning. It could be a 2 by 3, a 2 by 4. It would be necessary in order to do block multiplication via the partitions that the number of row partitions here in B is equal to the number of column partitions we have in A. So B3, B4. And this partitioning has certain theoretical applications that we'll see again in the future. It can be useful for proving various matrix theorems. It can also have some practical implications. It can allow you to multiply large matrices by breaking it down into a product of smaller matrices. But here, we can carry out the multiplication on a block basis. We could treat these as individual elements here. And so here in this first portion, we get A1, B1 carrying out multiplication of this row times this column plus A2, actually that's A3, isn't it? A3 times B2. And then similarly here we'd have A1 times B3 plus A3 times B4. Notice I'm being careful to do left multiplication by A or right multiplication by B. And then for this bottom part row here, we would have A2 times A4, A2 times B1 plus A4 times B2. And then for this last element, we'd have A2, B3 plus A4, B4. Now, when we partition this matrix, it has to be done so that the corresponding products exist. That means that, for example, the number of columns of A1 has to be equal to the number of rows of B1 in order for this product to exist. They have to have that same inner dimension. And similarly for A3 and B2, and then in order for this sum to exist, these corresponding product matrices would have to have the same dimension. So again, we'll see this in some future work that we do. I just wanted to point it out now because we will run into it again. Okay, let me clear the screen and talk about the last topic in this section. It's on directed graphs. So actually seen, and we'll be looking at again in the future. And our focus is primarily linear systems. We've seen how matrix multiplication can be used in the study of linear systems and in transformations. Another application is in a mathematical area known as graph theory. Graphs are useful in a number of different application areas, in particular in computer science, where they can be used to represent networks. So here's an example of a directed graph. A directed graph consists of multiple vertices or nodes. Okay, so here I'll show a directed graph. It's not complete yet, but it's got this particular vertice. Has this particular directed graph is going to have 3 vertices shown in circles here. Sometimes they're also called nodes. Excuse me. And then we have directed edges or lines between the different vertices. In this case, I'll show a double-headed arrow indicating that information, or whatever this represents, can pass from V1 to V2 and also from V2 to V1. But maybe we've only got a one-way path, or a one-way. You could think of this as a street, a one-way street between V2 and V3, and then similarly a one-way street from V1 to V3, and then V3 actually consists of some sort of loop back to itself. So in this case, this particular directed, it's called directed because the arrows here, the edges have arrows allowing flow in either both directions or in a single direction. But this particular directed graph has 1, 2, 3, 4 edges. Okay. Now, corresponding to a directed graph is what's known as an adjacency matrix. The adjacency matrix A for a graph with n vertices or nodes is of dimension n by n, so it's square. And then the aij element is 1 if there is a path from Vj to Vi. Okay. So corresponding to this directed graph, the corresponding adjacency matrix is, and then I find it helpful to put above each column. This is we'll have entries, non-zero entries here if there's a path from vertex 1 to the other n elements, and similarly in the second column, and then in the third. Now, this is not the same as, you wouldn't get the same result if you did this by rows, but this helps. The aij element is in the ith row and j column, so the paths go from the columns to the different rows, and so this helps me keep this straight. Another technique I've seen is actually to first come up with the adjacency matrix for the transpose, and then transpose that then to get the adjacency matrix A. But now, so how do we fill this out? Okay, if I look, the first element is from vertex 1, vertice 1 to vertice 1. There is no path from 1 to 1 like there is from 3 to 3 down here. Then I look, is there a path from 1 to 2? There is. Okay, and there's also a path from 1 to 3. Okay, notice the directed arrow there. So there is a path from 1 to 3. It's a double-headed arrow here, so I've got path from 1 to 2 as well as from 2 to 1. Now I look for from vertex or node 2 to the other nodes. Is there a path from 2 to 1? There is. Is there a path from 2 to 2? No. Is there a path from 2 to 3? Yes. So I put a 1 there. And finally, I look for from node 3 to the other nodes. Is there a path from node 3 to 1? There is not. Okay, there's a path from 1 to 3, but not from 3 to 1. There's not one from 3 to 2. And then finally, there is a path from 3 to 3. Now, this is useful because the number of paths of length r, and I got to prove this result, it's a fundamental result of graph theory, from node J to node I is equal to the ij element of a to the r power. Okay, now I'm going to take this opportunity to actually use octave to show you how to do matrix multiplication. So I'm going to enter this matrix A into octave, and then we'll compute a squared and a cubed. Again, it would be relatively easy to do this matrix multiplication by hand, but I want to show you how to actually do it in octave. So let me pull up octave, and then A is equal to, I'm going to enter in that matrix row by row, 0, 1, 0, semicolon, 1, 0, 0, semicolon, 1, 1, 1. Okay, and then close bracket. And then so here I've got my A matrix entered. It matches what I had on the previous board. And then now matrix multiplication in octave, I can do it as A times A to get, this would be A squared. Okay, notice A is 3 by 3, so I can multiply two square matrices of the same dimension. So A times A is defined. I can get a similar result by doing A squared. Okay, now by default, Octave, MATLAB wants to do matrix operations. So A squared is the matrix multiplication of A times A. Notice I get a different result if I do dot A squared. What this gives me is actually, let me pull up A again so we can compare A and A squared. A dot squared is the square of every element in A. Okay, so 1 squared is 1, but what I want is A squared or A cubed. Okay, A cubed is A times A times A. I get the same result there. So make sure that you do the corresponding matrix multiplication with a caret and then a 2 to get the squared, or a caret and a 3 to get A cubed. A lot faster than doing these matrix multiplications by hand. Of course, you can check any of your matrix multiplication results that we have for homework using Octave, and I'd encourage you to do that. It's a quick and easy check. Okay, so now let me go back to the whiteboard and write down what we have for actually A squared. It was 1, 0, 2, 0, 1, 2, 0, 0, 1, and then similarly we computed A cubed. I also could have computed A to the 4th or A to the 5th, but A cubed was 0, 1, 0, 1, 0, 0, 3, 3, 1. Now, what this represents, if I take a look at this particular element, again, this is from node 1 to other nodes, node 2 to other nodes, node 3 to the other nodes. So this tells me what the 2 here represents is that there are 2 paths of length 2, and this 2 corresponds to the power of the matrix here. Okay, that goes along with this 2. Okay, and then the elements in the matrix actually tell you how many paths of that specific length exist from, and the position tells us this is from node 1 to node, from node 1 or vertex 1 to node 3 in this case, column 1 to 1, 2, and 3. And then, so I should be able to find those. So 2 paths of length 2, one would actually be the V1, V2, V3 path. That's of length 2, it's got 2 edges. The other one is actually the V1 to V3, and then V3 can loop back to itself. This is the other path of length 2. And there are no other, at least according to graph theory, you shouldn't be able to find any other paths of length 2 from 1 to 3. This result tells me that there are only 2 paths. Similarly, if I look at, say, this element, this is 1 to n, 2 to n, and 3 to n. There's only one path. So this one corresponds to this one path of length 3. And the 3 there corresponds to the power. And then the position is, this is from node 2 to node 1. Okay. One path of length 3 from 2 to 1. Actually, if I go from 2 to 3, I can't get to 1. There's no path there. So that path would have to be V2 to V1, actually back to V2, and then to V1. So that's the 1, 2, 3 links, edges that are required to get from V2 to V1. And no other paths of length 3 exist. Similarly, we should be able to find 3 paths of length 3 between nodes 2 and 3. And I'll let you search for those. But I just wanted to point this out because it is another interesting, I think, application of matrix multiplication. It has some applications to computer networking theory. So this concludes all of the videos for today's lecture.